All right, welcome to The Explainer. Today, we are going to peel back the curtain on a really fascinating industrial process. Seriously, this thing turns heavy, almost useless gunk into things we use every single day. We're talking about everything from the oil in your car to the actual roads you drive on.
So, let's start with a really basic question. How does something boil? Now, you probably think, well, heat, obviously. But what if I told you there's another invisible force at play here that's maybe even more important? To get to the bottom of that, we have to look at this constant tug-of-war between pressure and heat. And trust me, understanding this relationship is the absolute key to everything we're about to cover. Okay, so we all learned in school about the boiling point of water, right? But here's the crucial detail most of us miss. Boiling isn't just about hitting a certain temperature. Nope, it happens at the exact moment a liquid's own internal vapor pressure gets strong enough to push back and win against the external pressure pushing down on it. Just think about it for a second. Water boils at a lower temperature on top of a mountain than it does at sea level. And why is that? It's simple. Less air pressure pushing down. It's really just a battle of pressures.
And this principle, this is everything. So on one hand, think about a pressure cooker, right? It traps steam, which cranks up the pressure inside, and what happens? The boiling point of water goes way up, and your food cooks way faster. But on the other hand, if you do the opposite, if you lower the external pressure, well, now you need a whole lot less heat to get something to boil. And that simple idea, that's the secret weapon we're talking about today.
So, why the big physics lesson? I mean, why does this even matter in the real world? Well, because it's the key to solving a very big, and honestly, a very sticky problem. What on earth do you do with all the leftovers from oil refining?
See, in a standard refinery, the first thing they do is something called atmospheric distillation. It works great for separating out the lighter, more valuable stuff, like gasoline and diesel. But once that's all done, you're left with this thick, heavy, gunky residue at the bottom. It's full of these huge, complex molecules that are still super valuable, but they are incredibly difficult to separate.
So the obvious solution seems pretty simple, doesn't it? If you want to boil off these heavy leftovers, why not just, crank up the furnace and blast it with a ton more heat?
Well, yeah, about that. Here's the problem. If you apply that much heat, you get something called thermal cracking. The temperature gets so extreme that it literally shatters those big, valuable molecules. It just breaks their chemical bonds and completely changes their structure. It basically ruins the product. And yeah, we definitely don't want that.
And this is where the real engineering genius comes into play. Instead of trying to brute force the issue with more heat, refiners came up with a much, much more elegant solution.
The whole idea is brilliant, really. If you can't raise the temperature without destroying everything, well, then just change the rules of the game. By dramatically reducing the pressure inside the distillation tower, you can get those heavy molecules to boil at a much lower, much safer temperature. And just like that, you completely avoid thermal cracking.
And this really illustrates the two choices perfectly. You've got the dangerous path on one side, just brute force it with heat and risk ruining the product. And then you have the smart path. Get clever and manipulate the pressure. I mean, for the engineers, the choice is pretty obvious, right? Okay, so how do they actually do this? Let's dive in and see how they create a giant vacuum inside one of these absolutely massive industrial towers. It's actually a pretty clever two-part process. So first, you have these powerful pumps and things called steam ejectors at the top, and they just pull air and vapor right out of the tower. That's what creates the vacuum. Then, and this is the cool part, they inject steam at the bottom. But get this, the steam isn't really for heat. It's there to help push the oil vapors up, which makes it even easier for them to boil and separate as they rise through the tower. All right, so after all this clever engineering, what's the payoff? What do we actually get out of it? What valuable stuff is created from that heavy, seemingly useless residue?
Well, this whole process neatly separates that residue into distinct, really valuable products, all based on their different boiling points. So the lightest vapors, they rise all the way to the top and become something called light vacuum gas oil, or LVGO for short. That stuff is used to make more gasoline. Then in the middle, you get heavy vacuum gas oil, HVGO, which is perfect for making things like lubricating oils. And then way down at the very bottom, the heaviest gunk that couldn't even vaporize, that becomes vacuum residue. And that is the key ingredient for the asphalt on our roads.
So there you have it. From sticky, useless waste to the very roads we drive on, it all comes from a super clever application of basic physics. Kind of makes you wonder, doesn't it?
What other invisible but totally ingenious industrial processes are out there, quietly powering our modern world, right under our noses?